In our upcoming video, we'll conduct a real-world performance test comparing the heat exchange efficiency of different steam traps, so you can have a clear and practical understanding and choose the most efficient type. Let me highlight some important points about steam traps. When installing, make sure that the steam inlet line is positioned above the heat exchanger and the steam trap is installed below the unit. This is because steam condenses into water, which naturally flows downward by gravity. Therefore, placing the trap at the lowest point ensures proper condensate collection. However, some special equipment may not follow this rule. In such cases, the system must be properly designed to prevent condensate from being trapped inside. A standard trap station must be installed completely. Never omit essential components. A proper trap set typically includes one steam trap with 2 isolation valves, a blowdown for cleaning and maintenance without shutting down the system, a check valve if multiple traps share a condensate line, an optional sight glass to observe the trap's operation, and a strainer installed before the trap for better protection, even if the trap already has an internal screen. When selecting a steam trap, the following factors should be considered. If the equipment has a control valve at the steam inlet, use a float-type trap with a built-in thermostatic air vent, which allows continuous condensate discharge and air removal. If the system has no control valve, such as steam main drains or header blowdown points, use thermodynamic or disc-type traps. For systems that require condensate to cool before discharge, a thermostatic trap is the best choice. For applications with steady, non-fluctuating loads, the inverted bucket trap is an efficient and durable solution. After determining the correct trap type, focus on 2 critical parameters: the condensate load and the differential pressure, delta P, across the trap. For fluctuating loads, select a trap with 2 to 3 times the required capacity. For example, if the condensate load is 100 liters per hour, select 200 to 300 liters per hour capacity. For steady loads, a 1.5 times safety margin is enough. The third factor, delta P, has a major impact on trap performance. Let's look at this example. A finned tube heat exchanger where steam flows inside the tubes and air outside. Steam enters at 8 bar, the pressure drop is 5 bar, condensate load is 200 liters per hour, and there's a control valve at the inlet. In this case, we select a float-type trap with thermostatic air vent, model FT series. The chart shown here is for FT14 traps. The x-axis represents the differential pressure, delta P, between the inlet and outlet. In this example, delta P equals 5 bar, 8 bar in, 3 bar out. The lines PMO 4.5, 10, and 14 indicate maximum operating pressure of each model. The y-axis shows the condensate discharge rate, kilograms per hour. At delta P equals 5 bar, draw a vertical line to the PMO 10 and PMO 14 curves. Then draw horizontally to find the discharge capacity. Skip PMO 4.5 because 5 bar delta, P exceeds its rated pressure. Results: FT14, PMO 10, approximately 700 kilograms per hour, FT14, PMO 14, approximately 350 kilograms per hour. Therefore, select FT14, PMO 10, providing triple the required capacity. Safe for high-load operation. Choosing PMO 14 instead would cut discharge by half, which can cause severe flooding under heavy load. Higher PMO ratings handle higher pressure but have smaller orifices, while lower PMO models have larger orifices and better discharge rates. Hence, the most expensive trap isn't always the best. It's about choosing the right type, right load, and right delta P for your system. In the next episode, we'll run live comparisons of common trap types, helping you see their actual performance and efficiency differences. Please stay tuned for our next video. Don't forget to like and subscribe to support DIVI Group. Thank you very much, and see you again soon.